This conference will now be recorded.
So we had started with alternating current, and we had learned so far what happens to the current and voltage relationship, phase relationship, if we apply AC voltage to a purely inductive circuit, purely capacitive circuit, and purely resistive circuit. So those things we have already learned. So today what we'll see, this is most important topic today we are discussing, because many questions, in fact, in various competitive exam, so this phase relationship and all those things will come. And among all these, LCR series circuit is one among the most important topic in this alternating current chapter. Okay, so today what we'll learn if we apply AC voltage. As you can see, AC source E has been connected with series LCR. Sometime you can draw the circuit like this, LCR, in this way also. This is drawn like from down to top. Doesn't matter. Only thing is you have to know what is series and what is parallel. So this is series circuit. This is L, C, and R. So this equivalent circuit is this one. Okay. So actually there are many good thing with parallel circuit also. LCR parallel, LR will be in series, and then C will be parallel. So these things are also there, but those are not included in your syllabus. If required, will for competitive exam we'll see sometime. So, but for today we'll be learning LCR series circuit. If we apply AC voltage to a series LCR circuit, so what is our agenda or aim today? Aim is to determine the instantaneous current in the circuit. So if I apply voltage, suppose this voltage is actually given as V is equal to Vm sine omega t. This is the source voltage. Okay, if we apply this sinusoidally varying source voltage to this series LCR circuit, so what will be the current? Instantaneous current. Okay, instantaneous current. So that we have to determine. And the second aim is that what is the phase relationship? Okay, phase relationship between instantaneous current, okay, and voltage, instantaneous voltage, or the applied voltage. So what is the phase relationship between these two? So what is, like, what are the aims here? First we have to determine the current, instantaneous current in the circuit, and then we have to find out the phase relationship between the current and the applied voltage. So applied voltage is this one. You look here, V is equal to Vm sin omega t, and we have to find out what is the current, how current is varying with time, whether it is sin omega t or it has some phase difference with the voltage. So that is what we have to find out. All right. So look, this problem we have to solve. So we have to find out instantaneous current. We have to find out the phase relationship between instantaneous current and voltage. So these are the two aims which we have to solve. Like these are two problems we have to solve. To solve, actually there are two methods To solve this problem, there are two methods. One is Phasor diagram method, another one is analytical method. So what is Phasor diagram method? If you remember, we had defined any sinusoidal voltage or any sinusoidal signal by rotating vector which will rotate anti-clockwise direction. So if you remember, we had learned what is phasor. Suppose you have a rotating vector, it can be current or voltage, and it rotates anti-clockwise direction with the same frequency as the voltage or the signal, and the magnitude of this vector will give you, sorry, the length of this vector will give you the magnitude at that particular parameter like voltage or current, and the projection, vertical projection, will give you the instantaneous value of that voltage or current. So that is what we have learned already, and we had drawn phasor diagrams for purely inductive circuit, purely capacitive circuit, and purely resistive circuit. So we have already experienced that just by phasor diagram, like in case of your purely resistive circuit, we have seen current and voltage, they don't have any phase difference. So current I and this voltage will be in the same direction with the same phase. So this is what we have learned already. So this is actually called phasor diagram method. So in this case also we can solve the problem by phasor diagram method, and another one is analytical method. That means you have to do differential equation. Okay, solve, you have to solve differential equation by some intuitive knowledge of this circuit, and then you have to find out the current. Okay, in both way we are just going to find out what is the current and what is the phase relationship between current and voltage. So this is our topics of discussion. So these are two topics. One is phasor diagram method, using which we can calculate the current in this circuit, LCR series circuit, when we apply an AC voltage to that series circuit. And another one is analytical method. Okay, so we'll try to cover these two today. So before we go to these methods, let me write the Kirchhoff's law, Kirchhoff's loop rule in this circuit. So if I write KVL or Kirchhoff's voltage law or loop rule, so if you write loop rule, Kirchhoff's loop rule, so this is what you get. That means the whole voltage across this source will be drawn by all of them. So if I know the voltage drawn by or EMF drawn by the resistor and voltage drawn by capacitor, voltage drawn by inductor, if we add all of them, we'll get the source voltage. Okay, in a closed loop we know voltage drop across each element. If you just sum all of them, that will be equal to the EMF of the battery or the voltage of the battery in this case. Okay, so from the Kirchhoff's loop rule, you can write this equation. So look, this one is the voltage drop across inductor L. This is voltage drop across the resistor, and this is the voltage drop across capacitor. This we know, right? So these are the things we have already learned. These things like how this is the voltage drop across the inductor, how this is the voltage drop. So this comes actually from your induction chapter. If you just recap this induction, see, like self induction will be self induction. This is called self induction. This will be phi is equal to Li. And if you want to write like get the EMF, then it is minus d phi by dt. Okay, d phi by dt, and so L di by dt. So this is how you get. And for capacitor, uh, capacitor, there is a relationship between capacitance, charge, and voltage drop across the plate of the capacitor, so that we know if the charge is Q stored in these two plates of the capacitor, then Q is equal to C, capacitance and voltage across this capacitor. So from here I can write voltage across the plates of the capacitor will be Q by C. Okay, so this is what we have got, Q by C, this one. And V is equal to IR from Ohm's law, that you know. So I'm not repeating that. So this equation, I hope you don't have any problem applying Kirchhoff's loop rule. Okay. Loop rule. So this is what we get. Now what we'll do, we'll just go to the Phasor diagram method to solve the problem. Okay. So let us go to Phasor diagram method. Okay. So just before we go for Phasor diagram for LCR circuit, we'll just recap what we have learned for individual L, individual R, like purely resistive circuit. What is the Phasor diagram for purely capacitive circuit? This will just recap shortly, because this will help us to draw the Phasor diagram for LCR series circuit. Okay, first we will just see the individual Phasor diagram. See, this is the Phasor diagram for a purely resistive circuit. That means you have only resistor. If you remember, so this is V is equal to Vm sin omega t. So in case of purely resistive circuit, the current and voltage, they have the same phase. Im sin omega t. They have the same phase. So that's why in the Phasor diagram, you look here, this part. See, the current and voltage phasor, always phasors are denoted by capital. So this is current phasor. Phasor means nothing but a rotating vector. Current phasor, and caps V is actually voltage phasor. Voltage phasor. Okay, so now see, we have already learned this, that these two are having the same phase, current and voltage. They have both of them actually have the same phase. So that's why in the Phasor diagram you look, we have drawn voltage and current phasor on the same line, and this is omega t. Okay, so this is the axis omega t, sorry, this is t axis. Okay, so you can see, you can understand, this is the current phasor, this is the voltage phasor. So what is the phase angle between these two? Phase angle, if I say phi between the current and voltage, in this case phase diagram is like phase difference is 0. So if you need to draw a phasor diagram with this, with the purely resistive circuit, you can draw current and voltage in the same direction. Okay, all right. So if I say the voltage drop across, how do you draw voltage drop across the capacitor? This is current and this voltage is the source voltage. Actually see, VR, this is the voltage drop across the resistor. This is nothing but Im into V. Okay, Im into V. Sorry, I'm into R. I'm into R. Okay. This VR will be actually I am into R. That means see the voltage drop across the resistor also has the same phase as the source voltage or as the current. Okay. So if you even draw, so this is V source voltage, this is VR. Okay. VR or the voltage drop across the resistor also in the same direction. Okay. All right. Now we have got phasor diagram for purely resistive circuit. Now we'll see how does the phasor diagram look for a purely inductive circuit. We have seen in case of inductive circuit, if you have this V is equal to Vm sine omega t, okay, and you have your voltage. See, you have equation L di dt is equal to Vm sine omega t, right? So if you just do integration of this, so you will get Vm by omega into L with a minus sign. So I will be this with a cos omega t. Okay, that means there is a, see, voltage is sine omega t and this is cos omega t. This can be written even, this cos omega t can be written as sine of omega t minus pi by 2. That means in this case inductive, so in case of inductor the current is actually lagging behind by 90 degree than the voltage. Okay, so the current in the inductor, if I write IL, this is the maximum current, and this will be sine omega t minus pi by 2. Okay, so the voltage is actually only sine omega t. Voltage has phase. See, this is the voltage Vm sine omega t, whereas you have this current. Okay, this is the current in the inductor. So you can see the current and voltage, they have 90 degree phase difference first of all, and the current is lagging. This lags behind. Okay, lags behind. Current lags behind. So that is why, see, look this phasor diagram here. The current is drawn over here. This one is the current, and this is the voltage. And what is the phase angle between them? This is the phase angle. That is 90 degree between current and voltage. Okay. So what is the phase angle? 90 degree. So 90 degree phase difference is there, and where current is lagging behind. So this is what we have to remember, that in case of inductive circuit, current and voltage, they have phase difference. Voltage means here applied voltage, phase difference 90 degree, and current is lagging behind the voltage. So this is what we have to remember. All right. So, and the last recap is that what is the phasor diagram for capacitive circuit? Okay. So if we remember that V is equal to Vm sine omega t, and the current in the circuit actually in the capacitive circuit, purely capacitive circuit, is Im sine of omega t plus pi by 2. I'm not deriving this. You just go back and look. We have already covered this. So the current is this. Okay. So you can see there is a phase difference. This is only omega t. This is omega t plus pi by 2. That means you have pi by 2 phase difference between the current and voltage. And you can see that this is with a plus sign. That means current is ahead of the voltage in case of purely capacitive circuit. So if this is the case, then you have to draw your voltage here. Okay, voltage is here and the current is here. Look here, the angle between this current and applied voltage is 90 degree again. So your current is ahead of the voltage in case of capacitive circuit. In case of inductive circuit, your current is lagging behind the voltage, and in this case current is leading over the voltage. Okay, so these are the things, few things you need to learn. Now just by recapping this, we have already understood how to draw the phasor diagram for individual circuit elements. For this is for R, purely resistive circuit. This is for purely inductive circuit. Okay, and this is for purely capacitive circuit. But now if we put all this together, LCR, okay, LCR, all this in series with a with an alternating voltage, then what happens to this phase diagram? Okay, so look, this is the phase diagram. This gives you the phase diagram, this one. So as we have discussed in the previous slide, the current and voltage for resistor. Okay, just before I just describe this phasor diagram, let me give you certain idea. In this case, same see, suppose at any instant of time, time t, the charge q is flowing through the circuit, or charge q is stored in the capacitor, and current I is flowing through each component. So this is the assumption we are doing. At any instant of time, charge stored in the capacitor is q, and the current flowing at, through all the because they are in series, so current I, the same current will flow through each of them. So this is the equation we get by applying Kirchhoff's loop rule. Now what we have to do, we have to draw the phasor diagram. Okay, so to draw the phasor diagram, what we are just assuming that our current, okay, so I'll just erase this. So suppose the current, instantaneous current is I is equal to Im sine omega t plus phi. That means, and you know the voltage we had the same voltage, sine omega t. So you can see from here that we have just assumed that there is a phase difference between the applied voltage and the current, and that phase difference is phi. The phase difference is phi. Now if I denote I is the phasor, current phasor, or this is current phasor, VR, this is the voltage across, so this is the phasor for voltage across R. Similarly, VL and VC, these are respectively the phasor. These are caps. Okay, okay. So these are caps. VL, VC, VR. So these are corresponding phasor for, this is for inductor, and this is for capacitor. Obviously this VR, VL and these are actually voltage drop across the resistor, inductor and capacitor. So I'm drawing the phasor of the voltage drop across each element. And in each case, the current and the voltage, they are in the same phase. That means your applied voltage and this phasor, like voltage, applied voltage and the voltage drop across the resistor will be having same phase difference phi. Similarly, since this is the current, so there will be phase difference between the voltage and this VL. This we already know, this will be 90 degree with VL. Okay, and with VC there will be phase difference again 90 degree with the applied voltage. Okay, since my current is omega t plus phi, we have to go with that. Look the phasor diagram over here. So we have the current has the phase omega t plus phi. So look, this is omega t plus phi you have taken, and this is the current phasor, and the current phasor and VR, current phasor and VR. VR means the phasor for the voltage across the capacitor, voltage drop across the capacitor. Sorry, voltage drop across the resistor. Okay, we know, we have already seen that voltage drop or the current in the resistive circuit and applied voltage, they don't have any phase difference. So in this case, the voltage and the current, they have phase difference. Voltage and current, they have phase difference. So omega t plus phi. That's why this I, that means, sorry, this, yeah. But there is no problem, no phase difference between I and VR. I mean to say, okay, I'll just write one by one, maybe. See, your VR can be written as Im into R. Then VL, this can be written as Im into XL. XL means this is the capacity, inductive reactance that you remember, I hope. And this is VC, this is Im into XC. This is the capacitive reactance, which is very much equivalent to the resistance in the resistive circuit. Okay, so now, so since these are actually, this is VL, this is VR, and this is VC. If we want to get the sum of this phasor vectors, look here, your VR is along the direction of current, so this has phase omega t plus phi, and with the current, this VL will be VL, it is actually having 90 degree. VL will be ahead, as we know, current lags behind in case of inductor circuit by 90 degrees. So that's why the VL is ahead here. And in case of capacitive circuit, purely capacitor circuit, as you can see from here, this is the V voltage which is leading over the current in case of inductor, and in case of capacitor, current leads. So current is ahead of voltage. So that is what we have drawn here. This is the voltage and this is the current. So current is ahead, and there is a phase angle between current and voltage is 90 degree. So that is what we knew, and this is how, if you are asked to draw, even in your board exam, if you are asked to draw the phase diagram for a series LCR circuit, then you have to draw this particular figure. Okay, and if you are asked to find out the current, instantaneous current in the circuit from this phasor diagram, what you have to do, you have to solve by vector method. You have to solve by vector addition. So these are vectors. These are all vectors. So now what we have got is, see, from this equation we can write this is phasor for, okay, this is a vector, okay, I can write, and this is VR vector, and this is VC vector, and this is actually V. This is the voltage across the source. This is the voltage across the source. Across the source. Okay, voltage across the source. So I hope you have understood this. With these are the voltage drop. This is voltage drop across this. I'm just writing from this equation. From this equation to this, I am writing. Okay, and since it is a rotating vector, all of them are rotating vector. Then I am just giving arrow head, okay, over the head. I am just giving arrow to denote these are vectors. Now if you want to calculate the current, instantaneous current, then you have to solve this by vector addition. So what we do here is nothing but vector addition. We'll do here vector addition, nothing else. Okay, nothing else we are doing here. Look, these two guys, they are actually in the same line, but they are opposite to each other. So if you have, so two vectors, this is VL and this is your VC, like this. So they are in the same direction. So what you can take? You can take the resultant of these two vectors. Okay. If you just take the resultant, here the resultant is this much, because this will be deducted somewhat from VC. You can see this is the vector, the resultant vector from these two, VL and VC. Okay. I'll just erase this part. Okay, so this is the, and see, you look, this the vector addition, it is written as vector addition VC plus VL, but this has magnitude, you have magnitude VS minus, sorry, VC minus VL. Okay, this has the magnitude of VC, that is the voltage drop across the capacitor minus voltage drop across the inductor. So this vector VC plus VL, this is a rotating vector, resultant rotating vector of VC and VL, or I can say resultant phasor vector between this, like and obtained out of this VL and VC just by vector addition. We have got from vector addition. Okay, all right. So what we are going to do here, we are just going to solve this problem by addition of vectors. Look here, this vector I can draw a parallel vector over here. Look here, this way. So this is the VCM minus VL. So this is the magnitude of the vector. You know, the length of the vector will give you the magnitude. So magnitude of this vector is VCM. VCM, this means maximum voltage drop across the capacitor. And this is VLM, maximum voltage drop, which you can write VCM. Actually, we should write IM into XC, and VLM we have to write IM, maximum current in the circuit, or the amplitude of the current into the capacitive and inductive or inductive reactance. You have to write like this. Okay, so this has got a magnitude of this VCM minus VLM, and this vector is actually a VR vector. That means the voltage drop across the resistor, and it has got magnitude VRM. That means voltage drop, maximum voltage drop, or the amplitude of the voltage drop across the resistor. So this is what the vector is. Now look, this problem is now have been simplified to a just vector addition problem. Look, you have a triangle over here. Now you have a triangle over here, so which you have, in which you have VRM, this vector. Okay, sorry, this vector is VR and magnitude is VRM. You have another vector, this is VC plus VL vector. This is a vector, you have to give notation vector. And look, this is the resultant vector, which is the source voltage V. Okay, this I can write as V. Okay, so this is now reduced to a vector addition by triangular rule. Okay, so what you can write from here, you can write that VR plus VC plus VL is equal to V vector. Okay, so this is what we had also written previously from this equation. Directly we had written, but now you can understand from this vector diagram from here. So you have the resultant vector V. This is the resultant vector. This is from triangular rule. We can write, and this is, you have this vector VC plus VL over here, and you have this as VR vector. So this, if you sum up, then you get the the hypotenuse of the triangle, this, which is actually the source voltage. I'll repeat it. See, you have now, what you have to do, you have to find out the net voltage. See here, you have VR vector, you have VC plus VL vector, this one, and this is, if you just think of a like a hypotenuse of this triangle, this is the source voltage, or the phasor for source voltage. So now we can write this as VR plus VC minus, sorry, VL plus vector I'm writing. So this is this one. Now if I write in terms of magnitude, look, this is what we'll be writing in terms of magnitude. If I just want to get the magnitude, what will be the magnitude? We know V is equal to Vm sine omega t. So we have got, see, like, if you get A plus B is equal to C vector, then magnitude, how do you write? If they are perpendicular to each other, or if they have some phase angle, you have to write C square is equal to under root A square plus B square. If this, and they are perpendicular to each other, this A and B, then we can write like that. Okay, so in this case, look, now we have to find out the resultant of this voltage. So we can write easily. So Vm square is equal to Vrm square plus Vcm minus Vlm square. So this is what we can write. Okay, and look here, in this case actually, if, so the resultant vector, this V, is making an angle phi with R. Okay, so this we can write as tan phi is equal to Vcm minus Vlm divided by Vrm. So this is what we can write as tan phi. Okay, so from there, or this can be in other way, you can write this Vcm is I, see, I am into Xc minus I am into XL. This is capacitive reactance, this is inductive reactance, and this is I am into R. So this Im goes off, then what you get is this Xc minus XL. So tan phi is equal to Xc minus XL divided by R. So this is also you can write. Now look, what we'll do is, we know from here, we'll try to write from there. We'll just erase this part. So what we have got is this, from this vector addition, Vrm square plus Vcm minus Vlm whole square. This is what we have got. So look, if I just write this as Im square r square. This will be writing, so Im square common. This will be xc minus xl whole square. Okay, this is what we can write. And look, if I just take this common, then you get r square plus xc minus xl whole square. Okay, this is what we get. Now, what was our agenda, if you remember? To find out instantaneous current. So the current here we are getting is amplitude of the current we will get as Im is equal to Vm. If I just simplify this, so Vm divided by under root r square plus xc minus xl whole square. Okay, and look this, I'll just erase this part. So look this part, this Im, I can write Im is equal to Vm by Z. So this Z is this one under root r square plus xc minus xl whole square. Okay, so this is called impedance. Impedance. What do you mean by impedance? Impedance actually is the equivalent resistance in the AC circuit. Like see, in your DC circuit resistance is R, but in your AC circuit there is something to resist the current, and that is impedance, which is equivalent to resistance in your DC circuit. Okay, so impedance is the resistance in AC circuit. What is impedance? Impedance is the resistance in the AC circuit, and it depends on frequency, because see, xc means omega into, sorry, 1 by omega into c. This is capacitive reactance where you have frequency of the AC signal, and xl also you have omega into l. So omega is the frequency of the signal. So you know this impedance, this resistance in the AC circuit is varying with frequency. Okay, varying with frequency. If your frequency is changed, then your impedance also changes. Okay, so you have to remember, in AC circuits there is an equivalent resistance which is called impedance, and that is given by under root resistance square plus xc minus xl whole square. This is in case of LCR series circuit. For an LCR series circuit you have impedance which can be written as this. Okay, so this C, because this is Vm voltage, maximum voltage of the battery or the AC source, and this has dimension of resistance. That's why you get the dimension of current over here. So that is why we are saying that this Z is equivalent to resistance. Okay, because Vm by Z, Vm by something which will give you the, like, which will make your this quantity as having dimension of current. So that's why this is equivalent resistance in the AC circuit. Okay, now we'll see. So if we draw this, this is called actually impedance diagram. Impedance diagram. This is very important. Okay, this is very important to know here. See the resistance or the difference between capacitive reactance and inductive reactance, that has been taken as one of the side of a right angle triangle. You say this is perpendicular. So if we draw R, or the resistance and the capacity, the difference between capacitive and inductive reactance in such a way that these two values will be becoming two sides of a rectangle, right angle triangle, and the impedance becomes the hypotenuse, then look what we can write. Tan phi from here we can write as perpendicular by base, which is R. Okay, so sometime you may need to find out cos phi, so this will be base by hypotenuse. Base is R by Z. If you need to find out what is sin phi, then you have to find out this is perpendicular by by hypotenuse Z. So these are the terms you need to know, which will be again useful in case of analytical method of solution. So look, you have understood right now what we have got. We have got the current expression for the current, or the maximum amplitude of the current, and we have seen the phase relationship phi, which can be given as tan phi, or phi can be written as actually tan inverse of xc minus xl divided by r. Okay, this is what you can write, or cos phi sin phi you can write similarly. Okay, so this is the method of Phasor diagram to find out the current and the phase relationship between current and voltage. So now if we want to learn what is the analytical method, I'll just start with the analytical method. Let me see how much we can cover analytical method. If I can cover the analytical method, we'll finish this today. Okay, we have got another 10 minutes. We'll try to finish this up today. So this is my LCR circuit, and you know, from Kirchhoff's voltage rule or loop rule, we have got that L di dt plus I R plus Q by C is equal to the voltage which is applied to this circuit. This is Vm sine omega t. So this is the V. So this is what we know. Now look, since these are in series circuit, so we are just learning the second method of finding out instantaneous current and the relationship between phase relationship between the current and voltage. So this is analytical method we are just going to learn now. Okay, analytical method. So this is the equation. You can see that as we have already discussed, suppose at any instant Q be the charge on C and I is the current which is flowing through each element. Okay, so what we will do is we'll just take arbitrarily Q the charge. Let us see, let us say the charge is oscillating because see this is the AC voltage, that's why charge also will be oscillating, or charge also will be alternating. The magnitude of the charge will be varying, not only magnitude as well as the direction also will be varying. Just since your voltage is varying, we know Q is equal to CV. C the capacitance is constant, but V is varying. So current, so the capacitance, the charge also will be oscillating in the circuit. So what we are doing is we are just taking arbitrarily that the charge at any instant of time Q V Q M, that is the amplitude of the charge, and how it is varying is sine omega t. plus theta. So suppose this is how it is varying. Now we know I is equal to dq by dt, right? So we have to we have to solve this differential equation. We have to solve this differential equation using this information that the charge is qm sin omega t plus theta. Let us see how we can do. We can just put this here because we know the current, because we have the current over here. So I know the current is this, so di dt will be double derivative of the charge, right? So now look, I'll just do the derivative. So q dq dt, which is I, because it is qm sin omega t plus theta, so you will get here qm omega, okay, qm omega, and this will be, sine will be going to cos of omega t plus theta. Now if you do the double derivative, that is di by dt, so which you have to do d2 by do d2q by dt square. So this you have to again derivative, you have to so take derivative of this equation with respect to time. So cos will go to sine, but with a minus sign, and you will get here omega square qm sine of omega t plus of theta. Okay, so this is what you will get over here. Now look, if I just put this equation a number and put this 2, this is, so this is 2 and this is 3. Look, I'll just erase the middle part. So I'll just substitute all this whatever we have got from here, we'll substitute here. So if we substitute here, so from, see, I'll substitute this. What is q? Q, we have got q m sine omega t plus theta. Okay, if this, so suppose this, you have 2, this you have 3, and this you have 4. So this 2, 3 and 4, this will be substituted here in the equation 1. If you substitute, what you get is, see, if you do it by yourself, you'll definitely get this one qm. Okay, so this I am just doing after certain simplifications. Okay, I'm just doing after certain simplifications. Look, what I can do is this qm omega. Okay, we'll get qm omega, then we'll get here. Okay, suppose this I am writing first. Okay, so I into r, I means qm omega into cos of omega t plus theta, so r into cos of omega t plus theta. Then if I write this thing, see, you have got this one. I'll write, let me write l di dt. What will you get actually? Only d. Okay, so you will get minus omega square l qm sine omega t plus theta. So this is what you will get. If you take common qm and omega, look, q and omega, so you will get omega into l over here. So I can just write, and you have already here minus, so you will get, I'll write as plus, but then I'll just give here minus omega into l, and along with that you will get sine of omega t plus of theta. Okay, this is what you will get for this guy. And for q, you will get So Q is QM omega. I'm taking common means 1 omega you have to divide. So you will get 1 by omega into C, and this will be sine of omega t plus of theta. Okay, you just do by yourself with a cool mind, you will get this thing. And if you just simplify a bit, then we can write this as Qm into omega, this as R cos of omega t plus theta, and this can be written as omega L means I can write XL, and this 1 by omega C, this guy I'll write XC. So I can write here XC minus XL into sine of omega t plus of theta. So this is what we can write. So I'll just erase the left part and I'll be using that space in the same page so that you can track this equation properly. Uh, Deepa and Selvi, kindly be another 5 minutes. I'll just derive this equation and then I'll left it there. And next day we'll be discussing the equation itself. Okay. So what we have got over here, look, we can write Qm omega R cos of omega t plus theta, and this we have got xc minus xl sine of omega t plus of theta. This is what we have got in the left hand side, and right hand side we have got Vm sine omega t. So this is what we have got. Okay. So if we, okay, we'll just write over here. So we have got Qm omega R cos of omega t plus theta, and then we have got here xc minus xl sine of omega t plus of theta, and right hand side was there the voltage Vm sine omega t plus of theta. Okay. Now look, we'll just do little bit of simplifications just by, see, we have got this z is equal to r square plus xc minus xl, and cos phi we know r by z. Okay, and sine phi, so this is cap z only. Sine phi we have got xc minus xl. This is what we have learned in the previous section, r by this by z. Okay, so if we just substitute these things over here, look, I am just dividing z with z, these guys. Okay, and here also we'll be dividing with z on the right hand side. Okay, right hand side will be dividing with z. So both side if we divide z, then look, this is r by z is cos phi. So you will get Qm omega, so cos phi into cos of omega t plus theta, and here it will be sine phi. This term will be sine phi, and this will be sine omega t plus of theta. Okay, and on the right hand side you will get Vm by z sine of, okay, right hand side there will be no so this is sine omega t. Okay, so if you use the identity of trigonometry, this particular thing you can write as Qm, okay, Qm omega cos of omega t plus theta minus of phi. So this is what you will get, and right hand side you get Vm by z sine of omega t. Okay, so I'll just take another 2-3 minutes Just don't get disappointed. I'm taking a little extra time today because we'll just finish this part, just calculation part, and then discussion we'll do on the next class. Okay, the calculation part. So what we have got is actually CQM omega cos of omega t plus theta minus phi after using trigonometric see sin a, see cos a cos b plus sin a sin b, so that is cos of a minus b. So that is what we have done over here. Okay, so if you know here, if so the identity you have used here, cos a cos b plus sin a sin b, sin a into sin b, so this you will get as cos of a minus b. So from there you will get it, cos of a minus b. So that is what we have written over here. And on the right hand side you had Vm by z, Vm by z sine of omega t. This is what you have got. Okay. Now if you want to compare these two, left and right hand side, you will get that Vm is equal to Qm omega z, and look, theta minus phi has to be pi by 2. Then you can compare this to sin omega t with this and this. So comparing both sides, okay, comparing both side of the equation, sides of the equation. Okay, if we compare, then we get these two corollaries. Okay, so that means what? That means theta will be phi minus pi by 2. Okay, now look, what we had taken arbitrary current is I is equal to Im sine of omega t plus theta we had taken, right? So this we can write now, sorry, from here, uh, from this above, just a minute. So this part actually we can write as current Qm, because this by Z we can write Qm into omega, we can write as current into C, Im into Z we can write this one. So we have got here C, this equation Im. So this is Im into this part. This part I will be writing theta minus pi as minus, sorry, this theta I'll be writing phi minus pi by 2. So you will get actually here sine of omega t plus phi. Okay, omega t plus phi only. So this is the current which we had to find out. Okay, so this is what we have got, the instantaneous current, and you look, there is a phase difference phi, and this phi can be written as tan inverse of xc minus xl divided by r. So this we have learned already. We have learned what is impedance, etc. We have learned. So I'll be stopping it here today. What we'll do in the next class, I'll just do little bit of discussion on this last part. What we have done, after the calculation, we have to discuss some things over here. So I'll do that in the next class, and then we'll take up new topic, resonance, on the next class. Okay, so obviously we need this LCR circuit. So we have many things to learn here with this LCR circuit, series circuit. So we'll be learning what is resonance and what is quality factor, etc. We'll be learning, and this circuit has a practical application in our day-to-day life, that also we'll be discussing. So that's where the resonance, etc. will be coming. Okay, so today I'll be stopping it here. Deepa and Guna, if you have any specific question, you can ask me for 2 minutes, or otherwise I'll stop it here. You can ask me on the next day also. Deepa, do you have any question so far what we have discussed today? What about Guna? Okay, so Guna is saying no, she doesn't have any question. I hope Deepa also doesn't have any question if she is not responding. Okay, so we'll stop it here for today. We'll meet again on Sunday. Okay, bye for today.